Essentially, when you're looking for the absolute error, just means the absolute value of the error. So it wasn't really anything special. It's just like the ones you did in the book, if you did those exercises where it talks about absolute error. Okay, but anyway, basically what you're doing is just using that same thing that you just did in the previous problem. So the same remainder theorem. And you're basically just using the x formula and putting in your 3/2 for x. You want to verify, of course, on that interval that you've got the same formula. So the z is the same choice, I guess, the same big M value. But you want to verify if that's the case or not. If not, you could change that a little bit and change the actual function of x. But otherwise, you just eventually then put the value in for x and see what your value is. Rather than checking an entire interval, you're just checking a specific value. Okay? So it's really supposed to be a really easy question at the end, but sort of a follow-up. But some of the people were asking questions about it. Okay, well, let's go ahead now and see if you came up with the formula, or maybe found it, for the sine of x. We saw last time that the Taylor series formula for cosine of x we could write by putting the -1 to the n for the alternating sign times x to the 2n. 2n gives us an even exponent every time. You put 0, 1, 2, 3, and so forth in there. You get the powers of 0, 2, 4, 6, and so on. And then the bottom's that same number, the exponent factorial. So 2n in parentheses factorial. It may have been colored for some of you, yeah. Okay, so what are we going to get for sine of x? We've got n equals 0 to infinity. We got an alternating sign, same way this time. -1 to the n. Is that still going to work? It's positive first when you put the 0 in. Okay, negative second when you put a 1 in, so on. Okay, good. Then it's going to be x to what power? Okay, that would be one choice, one possibility. 2n minus 1. Does that work with 0?
No, because then you get -1.
You get -1. So we want 2n plus 1. Okay, that will be the right direction to go, and will give us what we're looking for. So 2n minus 1 was odd. That was a good idea. But we want to just verify that it's going the right direction. So in this case, you put 0 in, you're going to get 2 times 0 plus 1, which will be 1. If you put 1 in, you're going to get 2 times 1 plus 1, which would be 3. If you put 2 in, you get 2 times 2, which is 4, plus 5, or plus 1 is 5, and so on. So you get the odd powers going on up. And then the bottom is just that same number, so it's going to be 2n plus 1 in parentheses factorial. All right, so this ends up being the formula for sine of x, and as we'll see today, although I'm not going to do it for this one, but as we could prove after what we do today, this converges on the entire real line, and the entire negative infinity to infinity. So basically, this is equal to the sine of x everywhere, for every value in the domain of sine of x. True for cosine x up here too, and in fact, e to the x, the formula we got for it, we're going to prove today that it actually, its domain in the series is the entire real line, that it works for everything. Converges everywhere. Okay, so far? These three, by the way, you want to basically have memorized. You don't want to have to redevelop them for the final. Okay, so you want to know, this is an odd function. We did talk about that. Made some sense. The sine of x is symmetric about the origin. And so we called it an odd function back in algebra class, and maybe didn't really understand fully why, but that was the term that was given to it. Here, we can sort of see why it makes sense. This is an odd function. It's made up of just odd-powered terms. Sort of interesting. Okay, and then cosine x being symmetric about the y-axis is an even function, and we learned that back there, and again, didn't really have a good sense of maybe why it was called an even function. But here we see that it's made up of only even powers as we go through this. So it's sort of interesting again. Okay, it's helpful. That is one way to remember which is which when it comes to having these two memorized. Okay, the pattern's pretty easy once you have that idea in mind. Remembering cosine of x is an even function. E to the x again? Yeah, that's a really easy one. It's just x to the n over n factorial. It's as simple as we could possibly have, almost. Okay, involving a Taylor series anyway. All right, so far, so that is what we have. And now what we want to do is move on to another handout. That one's right here. The other, on the example 4 in the back of the worksheet is on the video. Went through it, both what's there and additional example of how to use the remainder theorem on it, just as another place to try it out. All right, so here's where we start. So So it doesn't really have a title this time. It's because it's sort of in the middle of another packet, but I want to start here because this is the primary next thing I want to be sure we cover. So we're going to talk about this idea of radius convergence in a moment, but basically it's the same thing as I just said. Basically, infinite radius of convergence means that these series, e to the x, cosine x, and sine of x, the ones that represent it, are the same or equivalent to the functions they represent on the entire real line. And we're going to verify that for e to the x in a moment. Okay, we can use these functions to create Taylor series for other related functions using composition of functions, so putting something else inside of it, using multiplication of functions, addition of functions, and so on. Okay, now we're going to focus on composition of functions first, and really that's the main one I'm going to spend some time on, but it works great if you want to add them together. If you got e to the x plus cosine x, just add these together and add the terms together. You get one new series that will represent e to the x plus cosine x. Okay, sort of wild. Okay, but what we're going to do now is just represent here e to the x squared. To start with, why don't we get what e to the x is for a few terms? I think it's easier to see that sometimes when we do that this way. So equals, let's see, that was putting 0 in, 1, plus putting 1 in, we get x. Putting 2 in, we get x squared over 2, plus x cubed over 3 factorial, plus x to the 4th over 4 factorial. I'm just going to give you the pattern here, plus dot, dot, dot. This thing is not aligned at all. All right, so what we're going to do now is put x squared in there, and first of all, we'll put it into this series of terms that we've got here. So we're going to have equals, let's see, 1 plus, when we put x squared in for x, it's going to replace the x, right? Just like a normal composition of functions. So we have 1 plus x squared plus,
would it be x to the 4th then over?
well, not yet. This one will be x squared over 2 factorial plus x squared cubed over 3 factorial plus x squared to the 4th over 4 factorial plus dot, dot, dot. Now let's just think about what that would look like. The first term is going to stay the same. The second will stay the same. What does this one become?
X to the 4th over 2.
Okay, we'll leave the factorial in to get the pattern here. Again, you know what they are if we wanted to simplify this out. Plus x to the 6th over 3 factorial plus x to the 8th over 4 factorial plus dot, dot, dot. We end up with a new Taylor series that represents e to the x squared without having to go through the whole process of taking derivatives. Do you like this? Is this easier? It is, right? It's quite a bit easier. You've got to think about it. Oh, wow, it's sort of wild you can do that. But this is just like a regular old function, except for it has a series in it. Okay, it's essentially a very fancy polynomial that has a lot of terms on it. That's what we've got in each of these series. Okay, now what we can do is actually put this right into the series representation. So I'll actually move that up a little bit. So e to the x squared equals, putting it into the series representation, we got n equals 0 to infinity of, in place of x, we're going to put x squared to the n over n factorial. And that can be simplified. Let's see here. I'm running out of space. Put it down here. So n equals 0 to infinity. What does x to the second to the n simplify to? X to the 2n. You multiply the exponents over n factorial. Now, if you look at that, does that give you these terms? If you think about it. Put 0 in, you get x to the 0, which is 1, over 1 factorial, which is 1. 0 factorial, excuse me, which is 1. You put 1 in there, we get x to the 2 over x squared over 1 factorial, which is still 1 on the bottom, so x squared. And then you get 2 in there, you get x to the 4th over 2 factorial, and so on. So yeah, it works out.
What is 0 factorial? Is that 1?
0 factorial is defined to be 1. It's the oddball. It seems a little odd, strange. We talked a little bit about it the other day of why that might make some sense, having to do with choices and ways of ordering things and so on. One way to order 0 things. That's one way to think of it. A little odd to think about ordering 0 things. But all right, so that is one of them. Take a moment to try B. And if you have time, try C. They're very similar to each other here. All right, what is this one going to look like? E to the negative x. 1 plus negative x, and it helps to put some parentheses in here, plus negative x squared over...
Isn't it negative 1 because you're doing x to the...
Well, think about it. You're putting it into the function, right? The function up here, I have the term still up above, is 1 plus x squared over 2 factorial, and so on. So you got to notice that the 1 isn't going to change. Okay? So 1 plus a negative x squared over 2 factorial plus a negative x cubed over 3 factorial plus ... We'll keep it there. Let's simplify that and see what it looks like. That would be 1 minus x. The negative here, when you square it, you get rid of the negative, it becomes plus x squared over 2 factorial. This becomes, since it's cubed, a minus x cubed over 3 factorial plus ... What do we see this changed? It's the same terms except for we get in alternating series. Interesting. Okay, so we could say this is equal to n equals...
Plus x, negative x to the third over 3 factorial.
Why isn't this plus?
Why is it plus above it, though?
Well, it's plus because we were just replacing the x with a negative x, and then we simplified by bringing that negative out. Okay, we want to see that clearly, and you want to show that clearly when you're doing this in your homework or your test or your final exam or worksheet that you're going to do for me for tomorrow. All right, so let's see. N equals 0 to infinity. Here we're replacing the x with a negative x to the n over n factorial. Okay, so now what we want to think about is when you have a negative in there, that's really a negative 1 coefficient. To make it clearer, we can take that negative 1 coefficient. It's like you have negative 1 times x to the n. And we're going to bring that out. So we got n equals 0 to infinity. We've got negative 1 to the n times x to the n over n factorial.
Why does that matter, though? Can't you just leave it as negative x to the n over n factorial to show that it's an alternating series?
Well, to make it clear that it's an alternating series, it's clearer in this form. Okay, it's not absolutely required in this case, perhaps, to do so. And over here, it worked without simplifying it, right? But simplifying it makes it a little clearer what the form is. So whenever we can, we generally do simplify these to show the nice series that we come up with. Okay, now, e to the 5x, I'm going to skip over that just because we have some lack of time. I might come back and show that in a video or something, but I think you got the idea in terms of what we've got here. So now let's try one with cosine. Cosine, I've given you the terms, actually, to make it easier right here, and we've got the series. And here we've got x squared we're going to put into it. So putting x squared into cosine, we get 1 minus, let's see, x squared over 2 factorial plus x squared to the 4th over 4 factorial minus x squared to the 6th over 6 factorial plus ... Let's see, this one will simplify to 1 minus x to the 4th over 2 factorial plus x to the 8th over 4 factorial minus x to the 12th over 6 factorial plus ... All right, if we wanted to put this into the actual series here, let's see what that would be. We've got n equals 0 to infinity. And we got negative 1 to the n. That's not going to change at all. The x is replaced with x squared raised to the 2n over 2n factorial. Okay, now that can be simplified. Let's see if I can move this thing over a bit. This thing can be simplified to be the series n equals 0 to infinity. Negative 1 to the n doesn't change at all. But x can be rewritten as x to the 4n. That's right, over 2n quantity factorial. And we look at that and we see, yeah, these are just multiples of 4, aren't they? The powers that we get, which is what we see 4n does. It gives us multiples of 4. So again, what I've shown you is we can do something very interesting with these, composing functions and creating a Taylor series for something more interesting than what we started with. Let me do the next one. This is sort of interesting too. First of all, we're going to put 2x in, but let's do it directly into the series this time. So we've got x times... Yep, I still want to see that, I suppose. Good idea. All right, so we've got x times, we're going to put 2x in there. So let's see, it's n equals 0 to infinity, and I've got negative 1 to the n, and I'm going to put 2x in there to the 2n over 2n factorial. Okay, now that will be equal to let's see, x times, we'll leave the x out there for a moment longer here, 0 to infinity, negative 1 to the n. The 2 we might want to bring out, 2 to the 2n times x to the 2n over 2n factorial. Now, we really could simplify this. 2 to the 2n could be rewritten as 2 to the second to the n, right? 2 to the 2n. So that's equal to 4 to the n. That might be nice. And we can also bring the x in now. If we multiply that in, you're going to get one extra factor of x. What's that going to do to this exponent here? No. When you have another factor of x, so you're going to have x times x to the 2n. What are you going to do with those exponents? No, you don't get 3n. 2n plus 1. That's not another n, right? So does that make some sense? Okay, negative 1 to the n, 4 to the n, and then we've got x to the 2n plus 1, all over 2n factorial. So what you've been able to see here is we can actually multiply factors of x in to a series. And that's sort of interesting. Just again, showing what we can do, treating these like functions, and to come up with another Taylor series for a more complicated function. This one I may show you in a video. It takes a little bit of time, and it's not vital to what we're going to do next, but I'd like to show you that it can be done. Here we're going to actually take the series for e to the x and the series for cosine x and multiply the first terms together to see what the first terms will be in the series that represents this particular function, this product. We're not able to as easily come up with a formula for it unless we can see the pattern, but at least we can get the first number of terms and maybe just set up at least the series, what it's going to look like. At some point we have to stop multiplying, though. It's basically like a FOIL structure. Yeah?
For the B that you just did you we don't have to do that figuring out what 1 minus x to the 4th over 2 a factorial plus x to the 8th. We don't have to put it in?
I see what you're saying. So what I did this time, remember how we first put it in here, which I think is easier?
Yeah.
And it's helpful to show. I think if you're going to do this in the final, this is probably the way to go with it. Okay? But once you know what you're doing, you can put it directly into the series as we did second in this one. Right? This time I chose to do it first just to sort of shortcut the process and to save some space and time here. But you could certainly put this into the 2x into this, and then you could end up multiplying the x into it, and you'd see how it would actually change each of those terms by 1 power. It would increase each one by 1 power.
Was the breaking up of the 2x and stuff like that, and the breaking up of the 2, was that just to simplify? Because couldn't you leave it in that x to the...
Yeah, it was just to make it simpler. Really to show that what we're getting here is odd powers of x, right? And really that's helpful to see what the form is, not have the 2 sort of grouped with the x whenever we can do that. Okay, and so this is why we did it there. Also, this would make it a lot easier to do the, at least somewhat easier to do the ratio test on it when it's in this form, because you get things to cancel a bit easier when you have it in this form. All right, let's turn the paper over and take a look at the other side. This is what we're going to end up using, one of the things you're going to end up using in your homework tonight, so I want to make sure you get a good idea of how we can do this. So we're going to use Taylor series to evaluate a definite integral, to approximate a definite integral that we couldn't do another way. So what we're going to look at is this integral down here. Notice we've got integral from 0 to 1 of e to the negative x squared dx. It's a little clearer on your paper, I think, than it shows up here. But what's missing here that we would need in order to actually integrate this directly by hand? A factor of x. Okay, hopefully you're sort of studying for your final exam or maybe your retake of the first test, but that's where that would show up. You would need a factor of x in order to actually integrate this with our techniques that we know. So we're actually not able to come up with a nice technique to integrate this other than maybe use the Simpson's method or something, right? Some other numerical method. But we can actually use the first however many terms we want here. I think I said first 4 terms of the Taylor series that represents this function to integrate and get a pretty accurate result. And we're going to verify that in a few minutes. So first of all, what we want to do is come up with the Taylor series for e to the negative x squared. Notice this is slightly different than what we did last page, right, where we did x squared, e to the x squared. So we're going to use these terms. We're going to find out what e to the x squared is.
E to the negative x squared?
Excuse me, yes. E to the negative x squared is. So here we're going to plug that negative x squared in over x. We got 1 plus a negative x squared in parentheses plus a negative x squared over 2 factorial plus negative x squared cubed over 3 factorial. And let's see, find the Taylor series. We need to just put the plus dot 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 here. And that effectively is the Taylor series.
You don't need the fourth power also?
You don't have to have the fourth power here also. We need the first 4 terms down here, right? 1, 2, 3, 4. So I just counted off enough that I needed it in terms of what I need. If I want to really clean it up, which would be a good idea here, we could write what we get. 1, this is going to become minus x squared. This one, because it's an even power, is positive. It gets rid of the negative. We get x to the 4th over 2 factorial. This one becomes negative.
Get rid of the negative then?
This one does not. What's squared? The negative is there already. It's not being squared. It's just negative x squared. So that's still negative x squared. Okay, over here we have a negative x squared to the 3rd power. That negative is preserved. We get x to the 6th over 3 factorial plus dot dot dot. Now that we need anyway, but we could, here to give the actual answer to this part, give the actual series now. So n equals 0 to infinity. We're going to have an alternating sign. So we have negative 1 to the n. We have even powers, 2, 4, 6, and so on. So we know that's x to the 2n. Over in the bottom, it's just n factorial. This time, I just looked at what I came up with in terms and wrote it from that. Of course, putting it in is a little bit safer way to go, just to double check that we're getting it. But here, I just went for my terms and wrote the pattern down in terms of my series. Okay, now we're going to use the first 4 terms that we see here to get an approximation of this integral, this definite integral. So we're going to say approximately equal to the integral from 0 to 1 of, and we're going to take the Taylor polynomial essentially for this function, but we didn't have to go through the whole process of finding a Taylor polynomial. But the first 4 terms are effectively, in this case, a 6th degree Taylor polynomial approximating this function near what value?
We don't know.
Near 0. Because originally we did this whole thing based on e to the x near 0, right? So it ends up being around the same point, centered at the same point. That is sort of important.
So if you want to center it like, if it was centered at like 1, you would do 1 to the something?
Well, you'd have the x minus 1 factor in it then. And you can actually come up with an exact series, the Taylor series that represents e to the x that does have an x minus 1 factor in it. That would be centered about 1. Okay, so it can be done. We're going to focus on doing it about 0 for now to keep things simple. But let's go ahead and see what we end up with here. So our polynomial approximation of e to the negative x squared around near 0 is 1 minus x squared plus x to the 4th over 2. We're going to simplify that factorial now. Minus x to the 6th over 6. Now I think you'll like this part because you could have done this part in Calc 1, right? I hope so anyway. So we're going to just go ahead and integrate now. We end up with that's equal to antiderivative of 1 is x. Antiderivative of x squared or minus x squared is minus x cubed over 3 plus x to the 5th over 10 minus x to the 7th over, whatever 6 times 7 is. All right, that goes from 0 to 1. And let's see here. That will then, putting the 1 in, this is pretty straightforward. We like 1s and 0s. So we get 1 minus a 3rd plus a 10th minus 1 over 42. Minus, when you put 0 into these happen to all 0 out, right? So we have minus 0 to show we've checked it. And now all we have to do is combine those fractions on our calculator. And let me see if I can locate my notes sheet here for this. Oh, it's in here.
So if you were going to do it to the, say, the 5th...
So we got 26 over 35. Okay, let's get that as a decimal now, because it's an approximation, right? So exact values are a little bit of a strange thing in an approximation. So go ahead.
0.74286.
Great. Okay, now let's just go ahead and see what the calculator tells us is the quote-unquote exact value of this original integral. Okay, using its basic technique, not one of our numerical methods, but the FN int or the graphical method. So
isn't that even a little bit off?
it's going to be pretty good. They're using enough terms that they're able to get a value that's exact as many decimal places as they can show. Probably many more than that as well. So here, 0 to 1, e to the negative x squared dx, using the calculator, not one of the programs here, we end up with 0.74 what?
How do you use the FN again? What do you type it into the parentheses?
How do you use the problem? Okay, let me go ahead and go over to that.
Sorry, I'm just trying to remember to use the FN.
Let's see, it's down here, and hopefully that's coming. There we go. All right, so let me see here. I'm going to go to y equals. Well, actually, no, let's just go to second quit. We've got an F and int right there. Second, enter, or math 9, I think, is where we have to go. So I'm going to come over here and put in the function. This time the function was e to the negative x squared, right?
Yep.
Second, e to the parenthesis negative. We need to use that negative x squared, parentheses, comma, the variable x, comma, 0, the a value, comma, 1, the b value, parenthesis, and then let me get rid of that parenthesis and press enter. Okay, so then it gives us 0.74682, 0.74682. So let's go back and double check what we got here. I want to make sure we have the right value here anyways. So what do we have here? 0.74682, right? All right, so we got the decimal places, 5 decimal places of accuracy from our calculator. And now let's just move this down out of the way. We notice that we have almost to the nearest hundredth just by doing 4 terms of this Taylor series. Now, if we want to improve that, what will we do? Add more terms, and I'll bet you get a lot more accurate with just one more term. It's basically like a series gets more accurate as you keep adding terms to it. It's the same idea we have here. It's essentially the series being integrated, which you can actually do that term by term too, which is a little wild to think about, but we actually could do that here, and that would be another way to look at this. Yeah?
Just a question about the homework, because you remember you handed it to me yesterday, and it says first non-zero terms. Does that mean you simply skip over the 0 and go right to 1 and do 1
Well,
to 4?
if you were to do these from scratch for sine and cosine, remember that you have some 0 terms in the middle that get skipped?
Oh, okay.
That's the ones we're skipping over. So essentially, when you do it this way, you don't see any of the 0 terms. Does that make sense?
So basically in the homework you just want us to skip those 0 terms.
Well, if you were to regenerate it from scratch by doing the Taylor polynomials, all the derivatives, it alternates in the sine and cosine between 0 derivatives and non-zero derivatives. So it's the first non-zero ones. And again, when we set up the series for the sine of x as we have here, we don't actually include in this sum the terms that are zeroed out. We just include them, the ones that are the odd powers that we ended up keeping.
2, 4, 6, those would all be 0.
Yeah, they're all 0 terms we don't include. So that's what it means when it says skip the non-zero terms. All right, so let's go ahead and try this next one. Take a moment to try this part. So writing sine of x squared. And then we'll integrate that down below here. I'm giving you the first 4 terms up there. We're going to use the first 4 terms again there down below. Okay, the last thing I'm giving you is actually the homework sheet due tomorrow. You already have the other homework that you've been working on and thought was due today. But this new one is the one that's new, and it's very quick, just like what we're doing right now. 2 problems just to make sure you know how to do this process. And there are some problems like this in the book. There are many other exercises that do some of the other things we've been doing, but I focused our attention on these 2 examples of this kind of process. Let's go through what we have here. See what you've come up with so far. So let's see. For sine of x squared, we're going to end up with replacing x with x squared in there. We get x squared minus x squared cubed over 3 factorial plus x squared to the 5th over 5 factorial minus x squared to the 7th over 7 factorial plus dot, dot, dot. In this case, we can rewrite this now as x squared minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial plus dot, dot, dot. Okay, plugging in into the series, let's see, that's n equals 0 to infinity. We've got negative 1 to the n. We now put x squared in there to the 2n plus 1 over 2n plus 1 factorial. When we simplify that, we get n equals 0 to infinity. Negative 1 to the n staying the same. What happens to this 2 here? You multiply it into the exponent, so you get x to the 4n plus 2. I did not get that to look very, very good. Let me fix that a little bit. X to the 4n plus 2. Okay, over 2n plus 1 factorial. That's the same as it was before. So we got a nice Taylor series for it. What we really care about, though, for this problem, to be honest, is what we have right here. And you know what? I think we get a pretty good result here with the first 3 terms. So I'm going to just, to simplify the process and take a little less time, I'm going to put the first 3 terms here for what we're going to do for our notes. You can do the first 4 and see how much it improves the result. But in this case, it actually does pretty good. Anybody guess why it does pretty good with just 3 terms?
Because the last one is incredibly small.
Incredibly small, and that power is really big. We basically have the equivalent of a 10th degree Taylor polynomial, which is going out quite a ways, really, when it comes down to it. All right, so let's go ahead and see what we get here. This is going to be approximated by the integral from 0 to 1 of first three terms we're going to choose this time because it said 4, but we crossed it off and made 3. We got x squared minus x to the 6th over 6 plus x to the 10th over 5 factorial, which is 120. Okay, really that bottom number, I guess, is what really helps us out here a lot because that's making it really a small value. And on the interval from 0 to 1, anyway, that's a small number. If you go beyond that, of course, that grows pretty quickly because of the 10th power. All right, let's go ahead and see what we get here. Just doing our Calc 1 now. X squared, when we integrate that, we get x to the 3rd over 3 minus x to the 7th over 42. Okay, plus x to the 10 plus 1 is 11. And here you might pull your calculator out, right? 11 times 120. 1320. Okay, we're going to evaluate that from 0 to 1. Putting the 1 in there, we get 1/3 minus 1 over 42 plus 1 over 1320. Minus, we put 0 in there, they all zero out. So we end up with here, I don't think I even wrote a fraction equivalent this time. I just went to the decimal. We get 0.31028. Now what we'd like to do is try the calculator. So maybe move down a little bit here. By the calculator, we find that the integral from 0 to 1 of sine of x squared dx, which, by the way, we cannot do directly again because we don't have that factor of x out there. But that, using the calculator, is about 0.31027. And you can do this check on your calculator. But you can see here, at least with 3 terms, we can see they're slightly different. If we took 4 terms, you would not see this difference in 5 decimal places. It's going to be farther out. So we see that we didn't do too bad with 3 terms this time at approximating this definite integral. Does this make some sense? Joseph? You got a different number with your calculator? Did you get it in radian mode? That's a good thing to think about. When you're doing any calculus, it's in degree mode, then change it to radian mode. You got to be in radian mode if you want to do any calculus with trig functions. That's real important to remember. Otherwise, you can get really messed up results. If you're in degree mode, it'll give you really small values usually.
You do sine x squared comma x times 0 comma 1.
Yeah, make sure you get the x squared in parentheses. We can do it together if we need to here. You got the right answer now? Okay, this part wasn't meant to be hard, but we want to make sure we do know how to do it. Let's see if I turn this thing on here. Hello. It's funny how they make this thing time out. Just like our regular calculator. I turn it on over here. All right, so let's see. Second inner. And we're going to put in the function. So let's see, this was sine of x squared. We're going to get rid of the negative, comma x, comma 0, comma 1. 3.31027. Okay, same value. Notice again, your mode has to be radian. Okay. So any questions? Any other questions on this process? You think you could do that part by yourselves? Okay, that is due tomorrow, that worksheet. In addition to the other one you've been working on, the 2 videos that I sent out there should help you finish up anything that you've been unsure about. If you have questions, shoot an email to me or stop by my office. I'll be in my office from about noon to 2 today, and after 3:30 for another, I don't know exactly, I think maybe half an hour at least, maybe until 4:15. I think I've got a meeting. It's about 4:30 today. We've got 5 minutes left. What I gave you in addition to this is something I'm going to put into a video and talk about tomorrow too, but just in case you want to see this more in detail, I'm trying to save us some time tomorrow for some review in class. But basically what you've got here is an introduction to power series, which I've already been doing work with. The thing we haven't talked about is how to determine the domain of a power series. The domain of a power series is called its interval of convergence. And you can see some of this written up here. I think it's actually at the beginning of this one right here. So the value of A is called the center of the power series. You can sort of see a connection to the Taylor series, the center or the value it's expanded about. We've got this x minus A here. It's like our x minus C. This time I went consistent with the book, though, so you could read it more easily and see exactly what the things were. Down here, the domain of a power series is called its interval of convergence. This is basically or effectively just trying to see where the series converges by putting in various values of x. One of the videos I put together last night already talks about that interval of convergence. And in one of the examples we actually have right here, maybe I should jump down to this. The distance from A in the middle of this to the edge of the interval of convergence is called the radius of convergence. And that, for some functions like e to the x, is infinite. So everything works. For every other function, though, it's always going to converge on an interval that's got the same distance in both directions from the value we expanded the series about, which is sort of interesting. Okay, this is a series that we could talk about pretty quickly in terms of thinking about where it would converge. What we're trying to do is figure out what values of x will make this converge. So x to the k equals 0 to infinity. What does that look like? It looks like a series we worked with. A geometric series. Indeed it is. So using what you know about geometric series, what do you know x has to be in order for this series to converge? We need to have absolute value of x, right? Less than 1. X is the ratio. So boy, if we have a value of x that's equal to 1, that would be a problem, right? 1 plus 1 plus 1 plus 1 forever. It would diverge. It won't give us a value. But if x is less than 1, or actually between negative 1 and 1, we see that, in fact, this series will converge. So if the series converges, okay, so because it's a geoseries with this happening, this is the ratio. Now, what does this converge to? What's A equal to here? So here, R is equal to X. A equals what? 1. Okay, and R is equal to X. So what would this converge to? A is 1 over 1 minus R. R is X. This is what I actually went through the Taylor series for, coming up with it from scratch, from derivatives, in the video I did. But here we can see that treating it as a series starting on this side, we can actually see this is actually equal to 1 over 1 minus X when it converges. So the interval of convergence for this series, this power series, is negative 1, comma 1. Does it converge at negative 1? No, because that would be negative 1 plus negative 1 to the second power, and so on. It's going to keep alternating. It doesn't ever converge. At 1, does it converge? No. You always have to check the endpoints, by the way. And then the radius of convergence here, which we often call R, is equal to 1. Centered at 0? 1 either side is the radius of convergence. Okay, that's all the time we have today. I will give you a video that goes through the other several examples, plus you've got them all written out here. Try the problems in the book that are like this, and we'll talk about it a little bit more certainly tomorrow. But this is really a very important concept. It's our last new concept that we have to worry about, so I want to make sure that you've seen it and have some understanding of it. Let me know if you have other questions. Otherwise, good luck as you take your retests. Anybody still doing that today? I know some of you are. And let me know if you have questions. I'll see you guys tomorrow. Be sure to come again tomorrow. You're going to do the class evaluations. You're also going to be able to review and ask some questions. And we'll set up the review session on Monday that I emailed you about. I'm going to give you a review session on Monday either in the morning or the afternoon. Let me know by email if you'd like when that wouldn't work for you.